The next speaker is Gary Barnhard on sustainable lunar settlement design charrette, off-world anthropological space infrastructure settlement, OASIS, and this is the conference. Yes, and I guess
you need to allow sharing, please.
Absolutely.
Oh, sorry, there you're allowed now.
Okay. And let's see here. Let's see if this works. Portion the screen, share, and we'll go to.
Yes.
The trick is I have three huge screens or two huge screens, and I'm trying to get it to a level where you'll be able to see things appropriately. And should be almost there. Boom. Is that visible well on your screen?
That's good. Now, yes.
Okay, great. So my talk today is on the off-world anthropological space infrastructure settlement, OASIS, fostering cooperation, collaboration, and competition. For those that may not know me, I'm Gary Barnhard. I'm with both. I exist in a number of different capacities. I'm the president and CEO of the Space Development Foundation, the director of strategic relationships for the National Space Society, and the vice president of the Moon Village Association. The genesis of the OASIS project, it began in this case as a Kepler Space University initiative to develop a prototype simulation analog for sustainable lunar settlement. It's evolved into a cooperative, collaborative, and competitive space preliminary and conceptual engineering modeling endeavor. The principal objective is to explore how outcome-based programs driven by known science, systems engineering, and architectural design can maximize the probability of mission success. OASIS 2045 is also the name of the Moon Village Association Architectural Concepts and Considerations Working Group, which generated a series of case studies in those regards. And there are multiple other instances of the name in various habitation studies. The starting scenario that we're working with is that the signatories of the Artemis Accords, united in their collective determination, have set their sights on the successful development of sustainable off-world human settlements as a shared goal that must be realized. Furthermore, this goal is best served by a combination of cooperation, collaboration, and competition. This effort to architect, engineer, and implement anthropologically sound space infrastructure for settlement purposes is intended to support a realized arcology. For those that are not familiar with this, Paulo Soleri coined, the Italian-American architect coined that term, and it is representative of the understanding of the relationship between humans and the natural environment and the built environment. The project objectives are to manage cost, schedule, and technical risk of the same in a manner that allows it to be actualized within a decade. And the actualization can be by direct implementation or infusion in other nation state and commercial lunar infrastructure projects. We've split the OASIS activities into three phases. The first being analog and robotic testing on Earth and in space, where the science-driven requirements dominate. Phase one, in situ testing of the subscale elements and distributed systems where systems engineering-driven requirements dominate. In phase two, at scale development, where architecture-driven requirements tend to dominate. The science-driven requirements that address the physical conditions on the lunar surface, such as radiation, temperature, regolith material that make up the moon, must be established and verified based on ground truth as the highest priority, and the results cascade through all the subsequent phases. To give you a notion of the scale of things that have been discussed and what we're trying to aim for in terms of the phase 0, you're looking at getting to the point where you can enable on the order of 5 to 10 people. Phase 1, 10 to 50, and phase 2, 50 to 500. When we went through through the exercise of trying to understand how the science requirements are driving the design. This is a spiral design effort where we try and identify what the key characterizations are of the problem space, and then how do those requirements end up fitting into the what's the sensitivity, what matters about those requirements. And we've proceeded to layer through it at different levels of detail. Similarly, with respect to the systems engineering, there are some fundamental trades associated with launch mass versus functional mass, payload volumetrics, logistics and handling, how you provide for both EVR robotic compatibility, EVA compatibility, and IVA compatibility. You've got considerations with respect to structural dynamics and integrity, maintainability, reliability, availability, interoperability, and the definition of what constitutes the required distributed systems and the elements. One of the interesting challenges about this is that as we look at what the driving requirements are, how do we structure and organize these in a manner that enables us to better characterize what we know and what we know we don't know? And similarly, with respect to architectural design driving requirements, one of the key paradigms within architecture is the notion that form follows function, only except for when it doesn't. You can have and where this comes into play is that volumetrics must be reconciled with the extant conditions without compromising functionality, and the requirements must be aggregated to optimize for overall utility. The classic thing, an example of where form doesn't follow function is that if you look at some of the the architect Gary's work, you have buildings that are basically designed to confront the occupants with a different view of what a building is. And that's the purpose of the external structure. And yet it still functions on the inside to meet the requirements. So there's some play there. Again, this notion of arcology, and then the proven architectural design considerations and standards should be built on, not reinvented. And this notion of OASIS as a realized arcology, that means we have to understand what constitutes life, what constitutes the natural environment, and what constitutes the built environment. Turns out, just that little notion of life, humans are one of these blocks. It turns out we don't travel alone. We travel with our own biomes and all the other phylums. You have to be, have to end up being addressed if you're going to provide for life. Otherwise, we've got a problem. When you look at it in terms of the natural environment, you can what you're hopefully are starting to see here is there's a pattern. Basically, each one of these tiles, hexagonal tiles that we've laid out here, is an area where we are able to dive in and get some traction in terms of next level details as to what matters. And then there's a relationship that you can, once you have a better understanding of what's going on in each one of these areas, you can ask how do they relate to the adjacent or analogous areas. And then, with respect to, the built environment, how do you go through and follow through in a similar manner? And each one of these tiles represents something where we were able to make some level of traction with respect to characterizing what we know and what we know we don't know. And this speaks to that point, just dives down and looks at several different examples from the life side of things. Okay, there's a biome buffer requirements for cycle stabilization. Okay, that is a specific area where there is a significant amount of work that could be drawn upon. Okay, and again, we're not trying to reinvent the wheel here. What we're trying to do is create a framework where whatever discipline you're coming from, you can see where your work fits in. Again, in the with respect to the natural environment, regolith bearing capacity. Okay, they had to end up changing the footpad size of the lunar lander very quickly. Okay, very late in the design process because they ended up with better calculations in those regards. And then in terms of the built environment, how do you orchestrate something that allows you to, incrementally build on your capabilities as opposed to requiring some miracle to happen in between in the process? How are we doing time-wise? Okay. All right. Again, this slide just summarizes the driving requirements at the top level. Again, trying to go through and tweak it with some additional levels of detail. For example, when you think about architecturally from an arcology standpoint, you have a whole variety of spaces that you have to provide for, including open atrium space, provisions for convective air columns, scar for expansion, private, shared personal, work, group, and community spaces are all required. When we look at what needs to be done in phase 0, there's earth-based modeling and simulation of habitat in other environments using both analytical tools and the modular fabrication of analog habitats and other elements that allow testing of elements for form, fit, and function, and building in situ test elements and distributed system test articles to be sent to the lunar surface for the phase 1 activities. And on the spaceborne missions, anything that we can test out in low Earth orbit or in cislunar space, before we get to the moon, it's best to, at a certain point, simulating an environment becomes more complex than actually just going there and leveraging those resources. From looking at it in terms of the science investigation, manufacturability, testing, can you actually, reasonably make the parts that are required? Can they be reasonably assembled? Can they be reasonably transported? How do you go through and provide the essential support services on the lunar surface in terms of establishing a pervasively networked lunar surface environment, permanent communication structures, establishing ubiquitous ancillary services such as position, navigation, time, etc. And then the ability to go through and using robotic systems to get the environmental ground truth and explore the seismic properties of the lunar terrain and testing robotic operations and autonomous processes. When we proceed into phase 1, where it's more systems engineering driven, it concentrates on the in situ testing of subscale elements and distributed systems. And you go through and you find yourself identifying what is the minimum set of elements that you have to have, and what are what constitutes the distributed systems. And since your corners in a space environment, none of the corners are padded for you. You have to go through and much the same way that from a fire safety standpoint, check everything to make sure it has at least two exits and things of that nature. It turns out for all of your systems engineering requirements, you have to go through the equivalent of defining those heuristics and being able to ensure that they're accommodated in each element that ends up being required. And we're heading along there. As we proceed, into phase two with the architectural design requirements as key drivers, you need to be able to turn the architectural concept and philosophy, translating that into implementable structures. How you achieve a realized arcology is actually critical. In the United States, there was a public housing project called in Pruitt, Idaho, that was deemed so horrendous to live in that when it was blown up, by the local government, it was a special event. Okay, um, so that's a we want to avoid that. We want structures that people want to not just survive in but thrive in, and we need to uh, you know from the standpoint of the scale, as I indicated earlier. I think that if you're doing anything less than 50 people, you're not at the critical mass necessary to sustain such things. And in terms of the first increment, having it be scalable up to 500 people seems to be a reasonable approach. And we looked at that through multiple angles, including genetic diversity and a whole set of in skill sets required, things of that nature. For excuse me, the natural environment, it seems that the lava sky vents or pits are a resource that is keen to be used. There are examples from Mare Tranquilitas and Maris Hills, that seem to fit what we were, ending up looking for. And there's over 200 pits that have been cataloged so far. This is an example of one of the systems engineering, deeper dives. Basically after your first landing, you want a landing pad. And this is an approach that utilizes a combination of materials that are used terrestrially for stabilizing loose or mudded earth. In this particular case, through the use of stainless steel and various heating elements, as well as the blast effects from the rockets themselves, we can create a centering of the lunar surface within forms that keep the scale of the crystalline structure within the so-called cracking radii of the tiles. And so this represents an interesting possibility. Again, having a geometric pattern that could be where the mats could be unloaded, from a landed vehicle, ends up being a very useful approach to this. And this fits in as we look at both the Blue Origin and the SpaceX concepts for the cargo lunar lander systems. You see you end up, there's a progression that needs to exist when you start thinking about how you provide for a cargo carrier. And there's the terrestrial reality. Okay. Uh, you know, if you've already figured out how to make something work, in a big way, leverage it if you can. Okay. And, understand what you have to do differently. And so this is an example where we've looked into that, and you can see that it's actually not that far off what Blue Origin, has gone for. And arguably, if you're trying to build a thin wall pressure vessel, cutting out half of it to build a door, okay, is not a particularly bright idea with respect to your center of mass. And there's a whole series of things that you can do with respect to the starship that can actually take advantage of what makes sense in terms of your CG, your center of gravity, and things of that nature. There's a relationship between stowed volumes and deployed volumes that we ended up exploring. The in the to achieve both a structure that can fit within the anticipated shroud. In this case, we're looking at the numbers for the starship, and then be able to be deployed with a combination of static structure, unfurlable structure, and inflatable structure. And this is what I was referring to earlier on this. This is 2D tessellation. And what we went through, and so far we've defined 5 elements or classes of elements, including the habitat module elements. One of the things that we ended up adding, though, was essentially a space frame that ends up fitting around the habitat module elements, that expands as the element itself is both unfurled and inflated, so that you have mechanical hardpoints to connect that to other structures. And we are heading on down the line here. And so there's also a series of other elements that have to be sufficiently differentiated. We've gone and laid out what we know with respect to the distributed systems, the additional considerations with respect to each of the structural elements in terms of what we know in those regards. And it eventually you end up having to look deeper into this notion of tessellation, into relationship to 3D space frames. It turns out working with the tetrahedron, which is the most fundamental lock structure in 3 dimensions, and with the addition of certain expandable or contractible structural elements, you can go and have a range of both curved structures as well as flat structures in the space frames. This shows you the relationship between tessellation in 2D and tessellation in 3D. There's this notion of the kissing number. This is where we ended up in terms of the phase 1 elements, where you're effectively, as opposed to being in a lava tube, you're taking a nearby crater that's appropriately sized, and you're creating a tessellation of the elements with a canopy over the same for protection. What this led to in further observation was the need for what amounts to be connector nodes that can be relocated, and the fact that there is, in terms of the central module, you end up altering the scale, where there's a difference where for the central module, you actually have to construct something out of pieces to create the pressurized volume in situ, as opposed to something that is launched, stowed, and just unfurled and expanded.
5 minutes left.
Okay. And, this is just showing that you can have a tessellation of these. When you go further and go to 3D, you have to look at um, a range of considerations that lead you into this notion of tensegrity, where you're dealing with erectable structures, self-supporting and self-sustaining structures. This arrives at a 3D tessellation pattern where you're essentially building a you're starting off with a structural platform, only instead of it being at the base of a big hole that you've dug, it's actually proximate to the surface, and you're building in and you're building out, so that you always have a a sustainable environment from from the initial activity on. You're not requiring anything of the environment around you. You're In order to be able to survive, you're going through and constructing an environment where you can build a pressurized um, volume. From an architectural point of view, there's a set of key interfaces that have to be addressed. And when we need to explore the relationship between tensegrity structures, gossamer structures, and geodesics. Um, and what this ends up dealing with is we also have to address the issues of positive and negative space. This is a cross section of the schematic addressing how we cope with the sky vent volumetrics, light, and radiation. Again, you want everything you can to be be able to function, even if it essentially fail safe. Uh, in terms of passive systems, get as fancy as you want with advanced steels, but there's nothing like a bunch of regolith between you and radiation. Uh, to protect yourself. And so we've gone through and made assumptions here with respect to ways to ensure that there's an appropriate environment and a transition between the outside to a hangar bay environment to the habitat environment. This establishes the bridging structure that we identified. It happens to assume a 10-meter box truss, which conveniently the stowed payloads can fit in on a staging basis and be moved into the central core. We looked at the volumetrics. This is not intended to be a prescriptive design. It's to establish that a relationship needs to exist between these different aspects of space, in different elements, and we need to be able to explore, adjacency, connectivity, scale for each of these. The In the grand scheme of things, as I said, this is a cooperative and collaborative project. We need to translate all we know and can come to learn into a realized arcology for sustainable settlements in cislunar space and beyond. This can enable us to be the best stewards we can of our Earth and life as we know it, wherever we choose to provide for it. Thank you for this opportunity to present this stuff. The full slide deck, of course, will be shared. This is, multiple years worth of work of the different participants in this, at this point, leveraging a whole bunch of work that's gone on for many, many years. Thank you all for the opportunity to speak. And how are we?
Right on time. Unfortunately, there is really no space for questions there. But thank you for a very comprehensive discussion about this project, Harry.
Okay, I will to provide the slide deck as presented. I just email it to you.
Okay, we can do that. Yeah, the
Okay.
presentation as such is recorded, so it will be made available as well.
Okay, great. Thank you all very much.
Thank you.
Thank
So
you. That was
the next
amazing.